Hi, my name is Balázs Holzer from Budapest, Hungary, and welcome to my course on algorithms and data structures in Java. So first of all, let me tell a few words about myself. I'm from Budapest, Hungary, as I said earlier. I'm qualified as a physicist, and later on I decided to get a master's degree in applied mathematics. Currently I'm working as a software engineer at a multinational company. So let me tell a few words about what you are going to get from this course. We are going to talk about the main data structures, and then we are going to implement them from scratch in Java. So first, we are going to consider arrays. Then we are going to talk about linked lists, stacks and queues, binary search trees, then of course balanced trees such as the AVL or the red-black tree. We are going to be familiar with splay trees and binary heaps, and of course hash tables and tries in the end. It's very important that if you find your videos blurry, you just have to set it to an HD option as you would do it on YouTube. So thanks for joining my course. Let's get started. Hi, in this video we are going to talk about data structures in the main and of course why to use data structures. So let's get started. I'm sure that you have posed the question several times that why do we need data structures? Why is it so important to bother about the concrete implementation of the data structures and to study about the internal structures of data structures? Okay, so what are data structures for? Basically, data structures are to store data in an efficient way. And basically, the most important word in this sentence is the efficient. So, okay, we can store data in several ways, but it's very important that with the help of data structures, we are able to store data in a very efficient way. So, why to use data structures? Because we often have the intuition that we want to make an algorithm fast, then we have to optimize it. We have to write it in C++ or C, and it's going to be the fastest algorithm possible. We just have to avoid nested for loops and to make sure that we make every calculation as fast as possible. But basically, algorithms can be boosted up by proper data structures. And when I first met with data structures, it was quite counterintuitive to me that okay, with storing data in an efficient way, we can boost up algorithms such as the algorithm behind the GPS, shortest path algorithms, spanning trees, and so on. So data structures make sure that the running time will be better for an algorithm. I think a good example is the Facebook application. The engineers have to use proper data structures because more than 1 billion users are present on Facebook. So they have to manage such a vast amount of users that have to track their friends, have to track their posts, their likes and whatever. So the running time for manipulating such huge data does matter. For example, if we would like to sort 10 items, of course basically we could use bubble sort, we could use merge sort or whatever. Basically it doesn't matter. When we would like to sort 10 million data items, for example person in a country, then of course it does matter whether we are using bubble sort or merge sort. So basically when we have a huge data in these kinds of situations, it's going to be important what data structures we use, what sorting algorithms we use, how we manipulate the data and so on. So let's consider two important examples. First, the Dijkstra's shortest path algorithm. Without a proper data structure, a heap or a priority queue, the running time would be quadratic, so ordo n squared. So we would like to find the shortest path in a graph where the number of edges is equal to the n, then the time complexity of this algorithm is going to be ordo n squared. The priority queue approach makes sure that the running time will be far better, ordo n log n. And if we have a huge data set, so the n is equal to a great number, then of course it's going to be very important to use n log n algorithm instead of the n squared. Or for example, let's consider the other important algorithm. By the way, we are going to talk about these algorithms later. So for example, we would like to construct spanning trees. Then we can boost up the algorithm with the help of priority queues again. So the running time of the algorithms are determined by the data structures we use. And basically, that's why it is very, very important to use good underlying data structures. Thanks for watching. Hi, in this video, we are going to talk about abstract data types and basically what's the difference between abstract data types and data structures. So, let's get started. What is an abstract data type? Basically, this is the model or the logical description for a certain data structure. It is like a supertype in programming, in Java for example, an interface where we define that what's going to be the behavior, what methods we would like to implement. So we just define what methods and functions the data structure will have, so we define the basic behavior without the concrete implementation. We don't know that how the behavior is going to be implemented with the help of two for loops or while loops or nested if-else checks or whatsoever. We just know that, okay, what's going to be the behavior. What's very important is that it is just a model. The abstract data type doesn't specify the concrete implementation or the programming language. Basically, this is what the user knows. For example, we have the stack. We know that we would like to have three methods: the push method, the pop method, and the peek method. The push is going to add an item to the data structure. The pop is going to return and retrieve an item from the data structure, and the peek is going to return an item without removing it from the data structure. But we know nothing about the concrete implementation, that how are we going to store the items in the data structure, how we are going to implement the push method. We just know that push, pop and peek methods are needed, and basically this is why the abstract data types came to be, because it's going to define these behaviors. The data structures, on the other hand, are the concrete implementations, so the actual representations of the data. The aim is to be able to store and retrieve data in an efficient manner. What we are looking for: we would like to be able to insert and find items in ordo1, so constant time complexity, and we would like to be able to retrieve items in ordo1, constant time complexity as well. Of course, this is the best case scenario. Sometimes we are not able to reach this threshold and we are not able to do every operation in ordo1 time complexity, but this is what we are after. So for example, arrays, linked lists and binary trees are data structures. We have the concrete implementations. So we have the abstract data type, just the model, just the supertype, just the specification, and the data structures, the concrete implementations. So we have the stack abstract data types with the concrete behaviors. And we can implement stack with the help of array or linked list data structures. We have the queue abstract data type, and we could implement queue with the help of array and linked list data structure. We have the priority queue as an abstract data type, and the heap, the concrete implementation of the priority queue. We have dictionaries and hash maps and arrays as the underlying data structures. So it's very, very important that abstract data types and data structures are not independent from each other, in the sense that abstract data types are the specifications, and every abstract data type have an underlying data structure that's going to implement the behavior that has been specified in the abstract data types. So that's the difference between ADTs and data structures. Thanks for watching.